Hello, I'm going to go ahead and spend some time in this video walking you through the solutions for the review that you should have completed for your Chapter 8 test. So I'm just going to go ahead and jump right in. Number 1, we're told to graph the function and compare the graph to that of f of x is equal to x squared, or we're comparing it to the parent function. So I'll go ahead and sketch a graph of that parent function first, vertex at the origin, and then I'll follow my pattern, left 1, up 1, left 2, up 4, and then we could even go 3 and 9. And then we reflect on the right. So my parent function, f of x, is going to look something more or less like this. Now, h of x, we can graph it using transformations if we want, or we can find our vertex and then use patterns. Either way would be okay. So I'll go ahead and find my vertex, and then I'll use my pattern. So I know that my vertex is an x value of negative b over 2 times a. Here b is 0, so that's negative 0 over 2 times 2, which simplifies down to 0. Which means that the y value of my vertex is whatever I get when I plug in 0. So 2 times 0 squared minus 3 simplifies to negative 3. So my vertex is at 0, negative 3. My vertex would be here. Now my pattern is generally left 1, up 1. Left 2, up 4, and left 3, up 9. But our a value is multiplying all of those ups by 2, so I'm going to multiply by 2. So I'll be going up 2 instead, up 8, and up 18. And then we reflect on the right-hand side. So right 1, right 2, and right 3. So left 1, up 2, left 2, up 8, and left 3 up 18 goes off my graph, and then on the right I reflect, right 1 up 2, right 2 up 8, and then my graph looks something like this, and that is h of x. So if I'm comparing the two graphs, h of x was shifted down 3 units. So we just took this guy, went down 3 to get my vertex. And then on top of that, we changed the pattern. So, and there was a vertical stretch by 2. Vertical because we changed the ups, and stretched because we multiplied by 2. And that would be number 1. So number 2, I'll go ahead and erase and start over. Number 2, I've got my same parent function of x squared. So here would be the graph of that parent function, f of x is x squared. And I'm going to go ahead and graph g of x. Now there are no shifts here, so I do know that my vertex is going to be at the origin. If I had any sort of addition or subtraction, then my graph would be shifted. But here our vertex is just going to be at the origin since we just have our x squared term. So what we're going to do then is change my pattern by multiplying by negative 1/2. So left 1, up 1, left 2, up 4, left 3, up 9. So I'm going to multiply by a negative 1/2. That negative is going to change all of my ups to downs. So here I'm going down 1/2. Here I'm going down 2. Here I'm going down 9 times 1/2 is 4.5, 4.5. And then the same on the right. So my vertex is at the origin. I go left 1, down 1/2. Left 2, down 2, left 3, down 4.5, and then we reflect on the right-hand side. So my parabola looks more or less like this. So we didn't shift it at all, but we did reflect, meaning we flipped it over. So g of x is reflected vertically. And we also multiplied all of those ups by 1/2, which means that we did something vertically, either stretching it or compressing it. Since we multiplied by 1/2, which made my graph flatten out a little bit, this is what we call a vertical compression. So our graph is reflected vertically and compressed. vertically by 1/2. And then that brings us to number 3. So number 3, I will have again my parent function f of x. And to graph p of x, I'm going to use transformations. Here I see that I have a positive 1 with my x, which means that my vertex has an x value of -1, and then my y value is that -1. This is in what we call vertex form, so we can easily identify our vertex. So my vertex is going to be here. We shifted down 1, left 1. I'm actually going to go ahead and just start by writing that. So p of x is shifted down 1 and left 1. And then we're going to check out what happened to our pattern. So our pattern is generally left 1, up 1, left 2, up 4, left 3, up 9. But we're multiplying all of those ups by 1/2. It is a positive 1/2 this time, so we stay going up. So here I'm going up 1/2, up 2, and up 4.5. So left 1, up 1/2, left 2, up 2, left 3, up 4.5, 1, 2, 3, 4.5, and then we reflect on the right-hand side. So my graph is going to look something like this. So we shifted it and we compressed it vertically. So p of x is shifted down 1, left 1, and compressed vertically by 1/2. That brings us on to number 4. So consider the graph of f of x. Find the domain, range, and zeros of the function. So the domain is which x values we're allowed to use. Well, if I follow this graph along to the left, there's no boundary or no wall on the left-hand side. So my domain does not have a left bound, and if I follow the graph to the right, although it does move slowly, it can go to the right forever and ever and ever. So there is no bound on the left or the right. So the domain here, we have a couple ways we can write it. We can either say all real numbers, or we can say the domain is on the interval from -infinity to +infinity, meaning there's no boundary on the left and there's no boundary on the right. So either way that you choose to write it would be okay. For my range, we're looking now at y values. So going up, I do see that there's a cap on my y value, and going down, it looks like my graph can go down with my y values forever, so there's no lower bound. So that tells me that my range could be any y value that's less than 8, but we could also equal 8. The other way to write that using interval notation would be that there is no lower bound, so we can go to -infinity, but then when we go up for our y values, there is a cap, so the biggest my y value could be is 8, and then we use a bracket to say that we can actually equal 8. So either way you choose to write your domain and your range is fine. You can use interval notation, or we can use inequalities. Zeros are simply where our graph crosses the x-axis. So the zeros would be at 3 and 7. So I'm looking for the x values where our graph crosses the x-axis, and that is 3 and 7. So write a function of f in standard form. To do that, my goal is to write my function in this form. I'm going to start in vertex form, so f of x is equal to a times x minus h squared plus k. I know that my vertex is 5, 8, which means that h is going to be 5 and k is going to be 8. So f of x is equal to a times x minus 5 squared plus 8. And now I'm going to use one other point to help me determine the value of a. So I'll go ahead and select the point 3, 0. I will plug in a 3 for x and a 0 for y, and I will use that to determine the value of a. 0 equals a times -2 squared plus 8. So 0 is equal to, this multiplies to 4a plus 8. I will subtract my 8 over. negative 8 is equal to 4 times a, and then I divide both sides by 4 to find that a is equal to negative 2. So this tells me that my equation f of x in vertex form is negative 2 times x minus 5 squared plus 8. Now, unfortunately, they do ask us to write it in standard form, which means that we need to multiply everything out. So now I'll take what I have, and I'm going to work with it to multiply it out. So f of x is equal to negative 2 times x minus 5 squared plus 8. So I'll go ahead and multiply out my x minus 5. So x minus 5 times x minus 5 is going to give me x squared minus 10x plus 25 plus 8. I distribute my negative 2. So negative 2x squared plus 20x minus 50 plus 8. And then I combine my like terms. So f of x is equal to negative 2x squared plus 20x minus 42. So this would be our answer to part B, which is writing our function in standard form. Compare the graph to the graph of g of x is x squared, so our parent function. Well, it looks like we were shifted up 8. And then we were shifted to the right 5. Our vertex used to be here. Looking at my a value, I notice that a is negative 2, so there is a vertical reflection. And we multiplied all of our up values by 2, so there is a vertical stretch by 2. And that would be part C. My last one is to graph a h of x, which is equal to this function shown. So all that means that we are going to do is we are going to move our graph to the right 6. It's almost like we were using our vertex notation where x minus actually means we're moving to the right 6 and we have a positive 6 for our vertex. So this says we're going to take our f of x function, which is this blue graph here, and just move everything to the right 6, which is actually in this case going to go off my graph. But it would look something like this, no other changes, and this would be my h of x function. We'll go ahead and use zeros in number 5, 6, and 7 to graph our function, and then find domain and range. So that means I need to factor. Factoring, I've got 2x squared minus 4x plus 4, which gives me 2 times x minus 2 all squared. So my zeros are 2 and then 2, so 2 with a multiplicity of 2. And what that tells me is that my vertex is actually at 2, 0. So my vertex would be here, I moved to the right 2, and then I had no vertical shift. And then my pattern is that I multiply everything by 2, so there is a vertical stretch by 2. So my graph is going to look something like this. In number 6, my zeros are negative 5 and positive 1. So positive 1 and then negative 5 would be here, which means that my vertex must lie on the point directly in the middle, which would be negative 2. So to determine where the vertex is, I plug in a negative 2. So y is equal to negative 3 times negative 3, or 9. So my vertex is here, and my graph is going to look like this. And lastly, I factor. Oops, that should be a minus 1. And this factors down to 4 times x minus 1 and x plus 1. So my zeros are negative 1 and positive 1. And my vertex would be on that line where x is 0. So plugging in a 0, I find that my vertex is at the number negative 4. So my vertex is going to be here, and your graph will look like this. I will pick up the rest of our video in part 2.